Hello, my name is Konrad, and I'm a PhD student at ETH Zurich. Today I'm going to tell you a bit more about some of my recent work in which I ran a retrieval study for a Venus twin exoplanet in the context of the LIFE mission. For those of you who have never heard about the LIFE missions, the LIFE mission is a proposed mid-infrared space interferometer which aims at characterizing and detecting terrestrial exoplanets in the habitable zone around their host stars. If you want to learn more about the LIFE mission, I would like to refer you to the talks by Daniel Angerhausen, Felix Dannert, and also Eleonora Alay. So just briefly, I would like to talk about some previous results. And in this previous study, we estimated the minimal technical requirements for LIFE, driven by the goal of detecting methane in an Earth twin atmosphere. And this study gave us first estimates for these technical requirements, and we found that we will need to cover at least a wavelength range from 4 to 18.5 microns, a spectral resolution of 50, and a signal-to-noise ratio of 10 to 15 at 11 microns. Now in this study, we moved on to Venus. So you might ask, why do we even consider Venus? Well, first of all, Venus is also located in the habitable zone at the inner edge. So it is a possible candidate, or would be a possible candidate for life. Further, Venus is interesting because despite having similar size and mass, the atmosphere is completely different from Earth. And especially Venus has a cloudy atmosphere. So Venus has an opaque cloud layer which obscures the view of the lower atmosphere and the surface, also in the mid-infrared. So our previous assumption of a cloud-free atmosphere is definitely no longer valid for Venus. And then this is also the first, to our knowledge, Venus twin retrieval study. And furthermore, this Venus analysis allows us to test if the technical requirements for life that we determined previously are sufficient, and also to demonstrate that our retrieval framework is not biased towards Earth or an Earth twin. We would also like to answer how well we can characterize Venus despite the presence of clouds. And then a next question would be, could we infer the presence of clouds with life? And if yes, could we determine the cloud composition and also the cloud structure? And finally, an interesting question is also whether considering clouds or the cloud model we use has an impact on other retrieved parameters. So I would like to briefly talk about Venus's atmosphere. So as most of you will know, Venus has a very high surface temperature, but the temperature in the atmosphere decreases rapidly with altitude down to about 230 Kelvin or 0.1 bar. And at that point, the temperature is a bit more stable. And also at that point, Venus's atmosphere exhibits an opaque sulfuric acid cloud layer, which obscures the view of everything below. And this can also be seen if we look at Venus's mid-infrared thermal emission spectrum. So here in blue, we have Venus, and in green, we have Earth. And we see that Earth emits far more than Venus, because for Earth, we somehow see the surface or parts of the surface, which is warmer than this cloud deck in Venus, which has a temperature of about 230 Kelvin. So it looks cooler in the mid-infrared despite being warmer. And this is an effect of the clouds. So how do we model these clouds in our retrievals? Well, first of all, we estimate the cloud opacity via scattering, and our cloud model assumes 5 parameters. The first parameter is the pressure at the cloud top, and then the second parameter is the cloud thickness, so the pressure range we span. And then the next parameter is the cloud particle abundance, and then also the mean cloud particle size. So how big are these cloud particles on average? And the last parameter is the standard deviation of the size distribution of cloud particles, and we assume a log normal cloud particle size distribution. Then we assume that 3 to 5 are constant throughout the clouds, and we also assume that there are no clouds outside this pressure range. Then we pass this cloud model to our radiative transfer model, for which we use pretty retrans, and we further assume atmospheric composition of mainly CO2, but also very little water and carbon monoxide. And then for the cloud particles, we assume a mixture of 84% sulfuric acid and 16% H2O by weight. And finally, we parameterize Venus's pressure temperature profile via a third-order polynomial. And then we pass the spectra to LiveSim, which gives us an estimate for the observation noise we would expect with life, and LiveSim just accounts for astrophysical noise sources such as local zodiacal dust, exozodiacal dust, and stellar leakage. And then finally, we use our retrieval framework to basically fit atmospheric models to this input spectrum, and we fit 3 different models. One of them is basically the same as we use to generate the input spectrum, and then we try fitting a planet with water clouds just to see if we can determine the cloud particle, and then also a planet where we assume no clouds to see what happens. And then we fit these models using pi multinest, so nested sampling. Some of the results are shared by all retrievals. And first of all, the good thing is all retrievals retrieve a very high CO2 abundance and don't manage to retrieve water and CO, but this is not really bad because the abundances are quite low. But we managed to show that Venus's atmosphere is very likely dominated by CO2 in these retrievals. And then if we look at the retrieved upper structure of the atmosphere, this also seems to be somewhat robust, no matter which model we assume. So up to the point where the clouds start. And then in the next step, we compare the performances of the different models with each other, and we do this using Bayes factor. So this plot basically shows which model is preferred. Red means that the top model is preferred, and green means that the bottom model is preferred. And like the shading or how strong the color is just indicates how strong the preference is. So we see that when we compare cloud-free to the true model, so the opaque sulfuric acid, we see that at live resolutions, we prefer the cloud-free model. What this means is that at these live resolutions, basically the cloud-free model and the opaque sulfuric acid model yield a similar fit, so both fit the spectrum very well. However, our retrieval prefers the cloud-free model because it has less parameters. So the cloud-free model has 10 parameters and the cloudy model has 15 parameters. And now if we compare the water cloud fit to the sulfuric acid fit at live resolutions, we also see that there's not really a preference for either of the model. And this means that we could not tell what particle builds these clouds. But if we go to higher resolutions in both cases, we would arrive at the true model. So in order to characterize such a planet with life, we would likely have to go to a bit higher resolutions. And then finally, I'd just like to mention that there seems to be a significant model dependence for certain retrieved parameters, especially the radius. So this means that when interpreting the radius we get from a retrieval, we have to be very careful. So you see here, if we assume the no clouds model, we drastically overestimate the radius. If we assume the H2O clouds model, we underestimate the radius. So the radius seems to be a parameter that depends on the model choice for these cloud models. And then there are also certain other planetary parameters which seem to be somewhat robust and which we could likely rely on in retrievals. And one example would be the bond albedo. So just a brief summary of the take-home messages. First of all, we find that a basic characterization of Venus is possible with life. So we can determine the upper structure of the atmosphere, and we can tell that Venus has a CO2-dominated atmosphere. Then if we would like to analyze Venus's clouds, we will likely need a bit higher resolution and signal-to-noise ratio. And what we also find is that certain parameters seem to exhibit systematic deviances when we run these, depending on the model that we choose. Thank you very much for your attention. And if you have any questions, please feel free to contact me.